So, as we've seen, there are instances where you're trying to solve a matrix equation, something like AX equals B, but this matrix equation has no solution. So, put in other words, this vector B maybe is not in the column space of the matrix A. This vector B is maybe not in the range of the matrix A. So if you're in the situation where AX equals B has no solution, and it's not possible to actually create the vector B, is there a way to get as close as possible to B? Is there a way to produce an output, maybe call it B sub 0, that is as close to the desired output and the desired result as you can possibly get? So B represents what we would actually want, but something that is currently impossible to obtain. The vector B0 is an imperfect approximation to that result, but it's something that's actually attainable. The process that's used to produce this approximate, as close as possible alternative to the desired output B, that process is what's called least squares approximation. Least squares approximation. So here's an overview of the process, and then we'll demonstrate the process step by step in the context of a worked example. So the first step of the least squares approximation process is, of course, to verify that it's not possible to actually produce the output that you want to produce. Verify that AX equals B has no solution. So once you've verified that the B that you're trying to get is not actually attainable, then you begin the least squares approximation process. And that process begins by calculating the transpose of your matrix A. Let's go through these two steps in the context of this worked demonstration. If possible, solve the matrix equation AX equals B, where A is equal to 2, 4, 3, 0, negative 1, 1. And B is equal to 6, 3, 4. If it is possible to solve this matrix equation, go ahead and find that solution. However, if this equation does not have a solution, try to get as close as possible to this output vector B. Find a solution that will produce an output that is as close to B as we can possibly get. So to that end, let's go ahead and try to solve this equation normally and see if we get an actual real solution. So for example, I could do that by row reducing. I could augment my matrix with the output I'm trying to produce, 6, 3, 4. And I could, for example, do some row swapping to push that negative 1 up into the top position. And then I could do some row replacement. I could, for example, add 3 copies of the top row into the second row, and that would eliminate that 3 underneath the pivot. I could add 2 copies of the top row into the second row, giving me 0, 6, and 12 plus 6, 18. And then I could eliminate this value underneath the 3 here. If I, for example, add negative 2 copies of the second row into the third row, that will eliminate that 6, but then it's going to turn this final value into a negative 12. So because we've ended up with a pivot in the outputs column, because we've ended up with an equation that's essentially saying I need 0 to equal negative 12, this is impossible. And because it's impossible, we know that AX equals B doesn't have an actual solution. So it's impossible for us to attain the value that we actually really wanted. But let's try and get the next best thing. And let's try and produce an output that is as close to B as it can possibly get. To that end, the next step we're going to take is we're going to calculate the transpose of our matrix A. We're going to calculate A transpose. And let's remind ourselves that the job of A transpose is to take all the rows of A and turn them into columns. So for example, here, A transpose would have the column 2, 4. A transpose would have the column 3, 0. And A transpose would have the column -1, 1. So here is A transpose. And we're now going to use A transpose in two different ways to find the least squares approximation. The first thing I'm going to do with A transpose is I'm going to calculate the product A transpose times the original matrix A. So I'm going to take the matrix A transpose that we just found, and I'm going to multiply it by the original matrix A, row 2, 4, row 3, 0, row -1, and 1. I have this vector 2, 3, -1 essentially dotted with itself. So I get from that 4 plus 9 plus 1. 4 plus 9 plus 1 is 14. Then I have this vector 2, 3, -1 dotted with this vector 4, 0, 1. So that's 8 minus 1, that is 7. That's exactly the same dot product as what we just calculated. So it's going to be 7 again. And then we have 4, 0, 1 dotted with 4, 0, 1. So that dot product gives me a value of 17. So A transpose times A has given me a square 2 by 2 matrix. Now let's calculate A transpose times B. A transpose times B. Taking my A transpose matrix and multiplying it by the output vector that I wish I could get, A transpose B, 2, 3, -1, 4, 0, +1, and I was trying to get the output of 6, 3, 4. So if I go through with this matrix vector product, I'm dotting this row with this column. So I get 12 plus 9, 21. 21 minus 4 is 17. And then this row dotted with this column, 24 plus 4, result 28. Okay, what I'm going to do is I'm going to solve the matrix equation A transpose A times X equals A transpose B. I'm going to solve the matrix equation involving this modified matrix and this modified output vector. So on the left-hand side, the modified matrix 14, 7, 7, and 17. I want to multiply that by some matrix X, and in that process produce this modified output 17, 28. Just as before, we can solve this equation using row reduction. I can, for example, swap the two rows. If I swap the two rows, then I can cancel out this entry in the bottom left corner just by applying -2 copies of the first row down into the second row. That'll turn that 7 into a -14, which will cancel out. That'll turn 17 into -34. -34 combined with +7 will be -27. And then -2 copies of 28 combined with 17, it's going to give me a result of -39. And we can already see that this equation is going to have a solution because in this equation, all of our pivots have ended up on the left side of the bar as opposed to the right side of the bar. Certainly the solution is not going to be cute if I interpret these rows now in terms of x1 and x2. I get negative 27 x2 equals negative 39, which means x2 is equal to 39 over 27, which I think can be simplified to like 13 over 9 or something like that. And then if I plug that back into the equation coming from the first row of the matrix, 7x1 plus 17x2 equals 28, we're going to get another relatively messy solution. 7x1 plus 17 times 13 over 9 equals 28. Evidently, the solution works out to be x1 equals 31 over 63. So based on that, our least squares solution to this equation would be the vector x equals x1, which was 31 over 63, and x2, which was 13 over 9. This is the least squares solution, and then if we apply the matrix A to this least squares solution, that will produce the output that is as close as possible to the output B, which we originally wanted to achieve. So the closest attainable output to our desired output B is equal to A times the least squares solution, the matrix A times this vector 31 over 63, 13 over 9. I've been doing pretty well with my arithmetic up to this point in this video, but at this point I will just get Wolfram Alpha to do this matrix multiplication for me. If you go through with this matrix multiplication, the result is 142 over 21. 31 over 21, and 20 over 21. This is the output that is as close as possible to the original output B that we were trying to achieve, but this output is actually in the column space of the matrix A. This output is actually attainable. Now let's go to GeoGebra to help us to visualize what's going on in this problem. So on GeoGebra, this slanted blue plane represents the column space of our matrix A. The slanted blue plane represents all of the vectors that the matrix A is capable of producing. And we can see visually that the column space is spanned by these two black vectors. These black vectors are the first column of A and the second column of A, together spanning the column space. Now, the vector that we wanted to produce originally, the desired output B, is this blue vector pointing out straight here. And what we can see is that there's no way for us to produce this vector B because it visually lies outside of the column space of the matrix A. So because it was not possible to create the output B, we tried to create an output that was as close to B as possible. And that closest attainable output, that vector B naught that we just calculated, is the red vector that I've graphed right here. This red vector is the graph of the vector that we calculated in this move. And what we can see is that the red vector does lie in the column space of the matrix A. The red vector is in the span of these two columns. And the red vector is closer to B than any other vector that lies in this plane. This is basically as close to B as you can possibly get from all the vectors that lie in this column space. So this is the visualization of the calculation that we just did using the least squares method. Now, if you're curious about why the algorithm works, why this somewhat strange process involving A transpose works, to speak a little bit about some of the ideas that make this method function. The idea is that if you look at this picture, you can see that there's something like a projection going on, right? Essentially, what we have done is taken the output B that we wanted to produce, and it lies outside the column space of A. So what we've essentially done is projected that output onto the column space of A. And the projection of B onto that column space is the red vector B naught that was as close as possible to the desired output, but was actually attainable. So there's a projection happening in the least squares process, projecting B onto the column space. Now, we remember that when we do projections, there are all kinds of dot products happening in that calculation, right? When you project one vector onto another, there is a dot product of the vector who's being projected and the vector you're projecting onto. And then there are dot products between the onto vector and itself. So there are dot products happening up here, and there are dot products happening down here. Now, notice that those same dot products are kind of happening when we multiply A transpose by A and A transpose times B. When we multiply A transpose times A, we're taking the dot products of the columns of A with the other columns of A. And when we're taking A transpose times B, we're taking the dot products of the columns of A times the vector B. So this process of doing A transpose times A and A transpose times B, that process is getting us the dot products that would be involved in a projection, the kind of projection that's happening as we take our desired output and project it onto the column space to try and find the closest actual attainable vector that's in the column space. So that's a short word on what is kind of going on in this least squares process. So that concludes this video. In this video, we talked about the process of least squares approximation. And least squares approximation is a process that we use when we are trying to solve a matrix equation AX equals B. It doesn't have a solution, so we basically try to get the next best thing and try and generate an output that is as close to B as possible. To find this closest attainable output vector, we start by calculating the transpose of our matrix A. And then we use that transpose in a couple of different products, A transpose times A and A transpose times the vector B. Then we solve the matrix equation A transpose A times X equals A transpose B. This equation will have a solution. This equation will give you an actual vector x, and that vector x tells you how to generate the closest possible output to the desired original output b. If you multiply the matrix A by your least squares solution, you will get as close to b as you possibly can.